And welcome to AD Academy. In this video, we are going to talk about this mechanical system that consists of a spring and the damper. In the last video, I have just connected a single spring with this mass block. However, in this video, I have modified the same diagram with this damper. Now, to draw a block diagram for this spring and the damper mechanical system, we are going to follow exactly the same step that we have followed in the last video, which was drawing a free body diagram, then driving the equations, and then we'll draw a block diagram according to the equations that we will draw from the block diagram. So, now the first step to draw a block diagram is we are going to draw this block of a mass in the same way, and we're gonna apply this input force in whatever direction is provided in the original diagram. Now, to draw any other forces produced by the spring and the damper, that would be Fc and Fk, the direction will be determined when we'll understand how the spring and the damper is going to work. So for that, let's see that when the input force Fi is applied in this direction, the reactive force produced by the spring will push this block downward, and similarly the damper will push this block downward as well, which means these two forces are going to be downward direction. So now we can easily draw the direction of it, and we know Fc and Fk are pushing this block downward. We can also redraw this block diagram because we know that Fc and Fk are going downward, so we can take this direction as a common, and we can write down Fi and this single line representing the sum of Fk and Fc pushing this downward. Now, to draw any equations from it, first of all, we have to understand what is Fc, what is our Fk, and what is the net force, which was given name Fnet. Sorry, this is question mark Fk. Now, we're going to start from a very simple equation, which is F equals to ma. And because we are using the spring constant, we are using k times x. We are using damping coefficient c, so we know that the damping coefficient, the force produced by the damper, will be damping coefficient times the velocity. So let's give this equation number 1. This is our equation number 2, equation number 3. Now, so the fourth equation would be F net, and we know F net is equals to Fi minus Fc plus Fk. And we know that the reason of the minus here is the opposite direction of this reactive force, because as I explained in the last video, when any reactive force is in the opposite direction of the input original force, which is this one, will be in negative sign, and when the reactive force is in the same direction as the input original force, will be added in the original force, which means if Fi was in this direction and Fc plus Fk was also in this direction, then we'll do Fc plus Fk plus Fi, but that is not the situation, so we have to put this minus here. And now let's open this bracket, and we can write down this equation in F net equals to Fi minus Fc minus Fk, because this minus is going to multiply by this plus here, and we're going to have this minus here. So let's clear it up and make it clear, and let's give this equation number 4. Now we got our Fc, we got our F net. Now we have to find out Fk, and we know Fk is equal to the spring constant times the displacement, which is in this diagram is given about here, and the displacement is going to happen between this ground and this point, and at the ground point we know the displacement is 0, so we're just simply going to mention xe minus ground. I would prefer to write down in the example the ground in exams to be ground, because the teacher should know that you understand the concepts. So k times xe minus 0 will give us fk equals to k times xe, and this is our equation number 5. Now we go all our necessary equations to draw this block diagram, and I'm gonna just simply highlight the equation that we are going to use to draw the block diagram. As we are going to use the first one, we are going to use fc, we are going to use fnet, and this final equation fk. We will not use this equation h is equal to kx. The reason is I wrote this equation here just to tell you guys that how come I'm multiplying this k times xe here, because I'm using the Hooke's law as we're using the spring constant. So let's go and draw the block diagram for this one. As I explained in the last video, always start from the integral part, because we know that the displacement xe is a second derivative, because when we integrate the acceleration we will get the velocity, and when you will integrate the velocity you will obtain the displacement, which means the second derivative, the second function. So now to draw the block diagram, we are going to start from the integral part, and let's say this is the first integral. When we enter the acceleration we'll get the velocity, and when you will again integrate the velocity you will get a displacement, and let's give this name the same variable as it was given in our question, so xc. Now we got a here entering into the integral part. So now this a is coming from the equation number 1, which is here. But now what we have to do is a is coming out of the equation number 1, so we have to rearrange this equation. I'm going to use a different color. They just f equals to ma, and we know a equals to f over m. That's showing acceleration is equal to f times 1 over m. So a is showing here the resultant, so we're gonna multiply 1 over m with the force, so we'll have this this a. So that block actually representing f times 1 over m equals to a. I hope this thing cleared the point here. And we got this f, so this f here is actually a f net, so I'm just gonna write down n here to just represent this is f net. And we know f net is actually taken from equation number 4 here. So we know in f net we are having 3 forces, fi which is in positive, fc and fk are in negative. So we are just going to use a summation block here, and in that summation block I will put this fi which is positive. I'm gonna use one force which is minus fc and minus fk, and I know fc is coming from equation number 3, which is just about this fc is coming just from this equation, and in this equation I know it's spring coefficient, which is the damping coefficient times the velocity, and we're gonna pick this point for the velocity, multiply it with the damping coefficient and send it back to here as a negative feedback. And now the leftover is fk, and we know fk is taken from equation number 5, and in that equation we know is spring constant times the displacement xc, and we know spring constant is a k, which is a constant, so we're gonna pick this point and times it with the spring constant k and send it back here. And we know this is our output and that is our input. So that is a complete block diagram. I hope this question cleared some concepts, and it is very easy to solve this block diagram. And in the next video I will use two springs and two masses connected in series with each other, and hopefully that question will clarify some more concepts of you guys. This is my second video for my YouTube channel. I hope you understand this question. Please like, subscribe and comment on my channel, and I'm more than happy to for any advices that you guys can give me to improve these videos that you can understand in a better way. So please like, subscribe and comment, and give me any advices that I can make these videos better in the future, and I will see you in the next video. Thank you very much.